In this video, we will be looking at the final piece of the linear algebra portions of this course. Specifically, we are going to look at matrix operations, some special types of matrices and matrix decompositions. Specifically, within matrix decompositions, we will be looking at eigen decomposition. Now, all these ideas are ideas that you should have been already familiar with. Please remember, this is just a recapitulation of the kind of things that you need to know for this course. If time permits, we will look at greater physical interpretations of this, but by itself linear algebra is a vast subject. So, why are we looking at matrix decomposition, also known as matrix factorization? To remind you, in previous videos we had seen that matrices transform one vector to another. So, if you pre-multiply one vector by a matrix, you get another vector. Now, this has physical meanings which we will look at as we go on through these this lecture itself. So, typically as you remember, we deal with very high dimensional vectors and tensors within machine learning. You might recall that if you have a 60 cross 60 grayscale image, you can interpret it as if it is a single 3600 dimensional vector or one vector with 3600 components, pixel 1, pixel 2 up till pixel 3600. Okay. So, these are just examples of the size of vectors that you will be dealing with, which means we are actually dealing with very large matrices. So, if you have to convert an n cross 1 vector into another n cross 1 vector. So, if you have a vector v, let us say this is n cross 1 and this has to go to another vector, let us call it w, which is also n cross 1, you will have to pre-multiply by a matrix which is n cross n, okay. Which means if let us say n is 3600, then A is a 3600 cross 3600 matrix. Okay. Now, it is usually useful to understand what these components mean, and as it turns out in its original form it is kind of hard to understand. And just like for a number we typically take, let us say if you have something like 91, you would say 91 is 13 times 7, both of these are prime indivisible further factors. Similarly, it is useful to factorize a matrix itself, and you can think of an eigen decomposition or other decompositions that we will be talking about as simple decomposing one big thing into smaller things which we can understand a little bit better. It is also useful sometimes for a large matrix to be summarized by one or two or a fewer numbers, okay, rather than a large numbers. So, we had seen that norms, for example, for a matrix we often use, at least within this course we will be using the Frobenius norm. So, norm would be all these n cross n reduced to a single number. Okay. So, mapping from an n cross m or m cross n to a single number. Okay. So, that would be the norm. Another such measure is trace. All these are smaller measures, obviously they do not summarize the whole matrix. A determinant which you will be familiar with, eigenvalues, singular values, etc., are similar numbers which try to encapsulate some idea about what the matrix represents, as we will see later on in these slides. So, the first idea we are going to look at is what is called trace of a matrix. It is simple. A trace of a matrix is simply the sum of the diagonal elements of the matrix. Okay. So, it is sigma aii. So, if you have a matrix, let us say 1 2 3 4 5 6 7 8 9, then trace of this matrix A is 1 plus 2 plus 3, which is 6 as shown here. Now, the idea of trace you can use for non-square matrices also. So, let us say this is longer, you had 10 11 12 1 2 3 etc. You would still look at only aii, which are a11 a22 a33, it would still be 6. Okay. So, typically however we will be using trace for square matrices. So, the trace has certain properties. Trace of a plus b is trace of a plus trace of b. Trace of a times b is trace of b times a, even though even if AB is not equal to BA, the trace itself is a property that does not change, okay, when you commute the matrix product. Similarly, trace of A is the same as trace of A transpose, which directly follows from its definition. These are some useful properties. The next idea is that of a determinant of a matrix. Again, you will be very familiar with this. I just want to make the notation a little bit clear, nothing much else in this slide. So, we all know that if you take a 2 by 2 matrix, you can simply define the determinant as A11 A22 minus A21 A12, and that the determinant of a bigger matrix is using kind of a recursion idea. So, if you have something like A11 here, then and if we call this sub matrix A, then determinant of A is defined as a summation over the rows or columns. We can do it either way, as you know, minus 1 power I plus j Aij times determinant of this is the sub matrix. Okay. Again, this is something that is very familiar to you from school. Now, more importantly, the determinant actually represents the volume. So, if you interpret the first column, let us call it A11, A21, A1, N1. Okay. So, if we call this V1 vector, this as V2 vector, so on and so forth up till Vn vector for a square matrix, then so let us take a simple case. So, if I have 1, 2, 3, 4, I can now think of this as 2 vectors, the 1 2 vector V1 vector, another V2 vector. Okay. In that case, the determinant represents the area of this parallelogram. Okay. So, similarly, you can extend this to higher dimensions also. If you have 3 vectors, it will be the volume represented by those 3 vectors 4, 5, 6, you can start interpreting this as n dimensional volume. Okay. So, this has very interesting consequences, as we will see shortly. So, one thing is invertibility of a matrix. Again, as you know, A inverse is defined only if you have determinant of that matrix A as non-zero. Okay. So, A has a unique inverse if and only if determinant of A, which we will sometimes denote as if its absolute value, is not equal to 0. Now, this automatically means that the columns of A have to be linearly independent. How does this follow? So, remember, I will use the same example as last time. Suppose we have A11, A21 up till AN1, if we call this V1 vector, V2 vector is A12, so on and so forth, okay, AN2, and we have Vn vector which goes till ANN. Now, in case one of these columns, let us say this column, let us say Vn vector could be written as a linear combination of these, okay, was some alpha 1 V1 plus alpha 2 V2 up till alpha n minus 1 Vn minus 1. Then what does this mean? By simply doing an operation of nth column goes to nth column minus this thing, you will get all zeros. Okay. This transformation, as you know, preserves the determinant, which means the determinant will become 0. Okay. This also has a nice physical interpretation. What it says is, if you have one of these vectors which can be represented as a linear combination of the other vectors, the volume of the thing formed by of the parallelogram or the parallelepiped formed by these vectors actually becomes 0. You can see this easily in the 2D case or even in the 3D case. So, let us say you have two vectors, in this case you only have a 2 by 2 matrix. Okay. In case one of them is linearly dependent on the other, it simply means that both these vectors or one of these vectors, let us say V 2 is equal to 2 V 1, then the area formed by these two vectors is simply going to be 0. Okay. You are going to get non-zero area only if one of them is not simply a scaling of the other. Similarly, if you have three vectors, if one of them is the linear combination of the other two vectors, it means all three are in the same plane, which means they are not going to form a non-zero volume. Okay. So, there are multiple interpretations for A inverse existing, and there are deep connections with the determinant of the matrix. Okay. So, we will now look at some special matrices and vectors, again this should be familiar for you. The first idea is that of a diagonal matrix. A diagonal matrix is one where only the diagonal entries are non-zero. Okay. All other off diagonal entries are 0. So, mathematically Dij, if D is the matrix, is equal to 0 if I is not equal to j. Okay. A symmetric matrix is a matrix which has, you know, it is symmetric across the diagonal. Another way to say it is that the matrix is equal to its own transpose. A unit vector is a vector with, as all of us are familiar, unit length. Okay. In our notation, which we remember, we had used the idea of a norm for length. So, typically norm of that vector is equal to 1, which norm, if you ask, typically when we say unit vector we mean the 2 norm. Okay. Please remember the 2 norm or L2 norm is simply V 1 square plus V 2 square, so on and so forth up till V n square root. Okay. But you can define a unit vector with norm 1 etc., but it is usually the 2 norm that we use. Another usual useful idea is that of orthogonal vectors. It simply means vectors that are mutually perpendicular, which means x, if x and y are mutually orthogonal, it means x dot y is 0, which remember can be written in this matrix form. You take x transpose y and set that equal to 0. We also have the idea of orthonormal vectors or orthonormal vector set, okay, where you have unit vectors that are perpendicular to each other. A orthogonal matrix is a matrix whose transpose and inverse are the same thing, okay, which means A transpose is equal to A inverse. The simplest sort of orthogonal matrix is the identity matrix. Okay. It has some nice properties which we will discuss very shortly, but a simple thing that follows from it is that A transpose A and A transpose is equal to I. This also means that all columns are orthonormal. Okay. So, remember if A is equal to A transpose is equal to A inverse, when you multiply the matrix by its transpose, you are actually going to get quantities of this sort which have to be 0 if x and y are not the same. Now, where do we use orthogonal matrix? Even though this is orthonormal column vectors, we still call it orthogonal matrix. Okay. An orthogonal matrix typically can always be thought of as a rotational operation. Okay. What that means is, if I have one vector, I pre-multiply it by something and all it does to that vector is simply rotates it without changing the length, the matrix which would have been used would always be orthogonal. This can be proved, we will not have time to show all that, but please do remember it. Whenever you see an orthogonal matrix, please think a rotation matrix. Okay. That is another way to think about it. So, let us now come to the matrix factorization that I was talking about, eigen decomposition. This is typically very useful for square symmetric matrices, especially square symmetric real matrices, even though you can use it for other matrices as well, and I am sure you would have done it before. As far as this course is concerned, we will primarily be using it for square symmetric matrices, and it has we are guaranteed several things when symmetric matrices when we have square symmetric matrices as far as eigen decomposition is concerned. So, here is the simple physical meaning that is usually useful in order for you to anchor yourself in the eigen decomposition. So, every real matrix, remember I have talked about this before too. If you have a matrix A, what it can do, for now I will talk only about square matrices. So, if you have a matrix A, if it multiplies pre-multiplies a vector V, it results in some other vector W. Now, you can think of A as a machine or an operator acting on V and giving you W, takes V, takes it to W. Okay. So, let us say this is the vector V, this is some vector W, and A has taken V to W. Now, through physics as well as intuitively, you can see that there are only two things that this matrix A can do to V. It can rotate it, that is, it can turn it through an angle, even in 2D, 3D, in any place that you can think of, it can turn it through an angle, and the other thing it can do is it can change its length. Okay. So, the length of V might not be the same as length of W, but it can stretch it, rotate it, or rotate it and stretch it. These are the two operations that any matrix can do as far as acting on another vector is concerned. Now, this is extremely useful. Now, if you can think of every operation as if it is a matrix, then there are special vectors, and the only thing that matrix will do to this vector is just stretch it. Eigenvectors are those special vectors. So, you are given a matrix A, and there are a set of special vectors for that, which we will again call V, eigenvectors, which will only stretch under the action of this matrix. What is an eigenvalue? Eigenvalue is the factor by which this vector stretches. Okay. So, mathematically I would write A times V is a new vector, this is the new vector W, but this W is not rotated, it is only stretched. So, eigen decomposition is that angle in some sense or that set of vectors which only stretch under the action of the matrix A. This is the physical interpretation. Okay. So, let us say, so we will now write the eigen decomposition. You can think of eigenvectors in some literal sense. Eigenvectors are essentially the coordinate system in which the matrix A looks the nicest, it looks diagonal. Okay. This is one way of looking at it. If you do not understand this fact, that is okay, I will just write the mathematical expression right now. Okay. So, let us say A has n linearly independent eigenvectors. Okay. That is, A is a n cross n matrix and it has n linearly independent eigenvectors V1 through Vn. Okay. Now, we will do what we have been doing so far. I will write V1 as if it is the first column, V2 as if it is the second column. Remember, V itself is a vector, therefore, it has n components, and we will go till Vn, which also has n components. Now, you concatenate or put them together and you get one large matrix, the eigenvector matrix V. So, this notation here, if you have a curly bracket, it is a set. If I put this, I have put them together, there is no comma separating this, this is actually a set of numbers put together as a matrix. Now, similarly, if each of these has a corresponding eigen value lambda 1, lambda 2, lambda n, and I put them together into one giant matrix lambda, which is a diagonal matrix, remember it is a diagonal matrix. So, all off diagonal elements are 0. then we can write the factorization of A as A can be written as a product of 3 matrices V multiplied by this diagonal matrix lambda multiplied by V inverse. Physically what it means is we have sort of rotated into the coordinate system which is defined by all these eigenvectors, and these eigenvectors purely do stretching. Okay. So, as I said before, all matrices can be thought of as rotating and stretching vectors. Eigenvectors are those vectors that are simply purely stretching. Okay. Now, what we know is real symmetric matrices, and this is where we will use them, have real eigenvectors and real eigenvalues. Okay. This is not necessarily true of all matrices. Even if you have a real matrix and it is not symmetric, it might or might not have real eigenvectors and real eigenvalues. Okay. In case you do have a symmetric matrix, there is a nice factorization for it. Remember, we had V lambda V inverse. In the case of a real symmetric matrix, you can write it as Q lambda Q transpose, where Q transpose would be the same as Q inverse, which means Q is orthogonal. That was our definition of an orthogonal matrix, which also means Q is a rotation matrix. So, physically what this means, what this factorization means is, so if I have A V and I am trying to determine what the action of this matrix A is on V, and let us say A is a symmetric matrix. We know from here that I can write it as Q lambda Q transpose V. Okay. So, let us say we have some eigenvalues or and eigenvectors. What this action does, what Q transpose V does is it rotates V into the direction of the eigenvector. Okay. So, that is what it basically does. Okay. So, you have two actions going on, there is rotation and then there is stretching. So, what the eigen factorization does cleverly is, this rotation is first rotated into the eigenvector directions, then you stretch it through the lambda, and after that you rotate it back, so that the net rotation and the net stretching are put together into one matrix A, and which can be written as Q lambda Q transpose. Okay. So, this of course will take a lot of visualization. I just sort of summarized it. If time permits, we will give some bonus videos towards the end of this course, so that you can visualize it too, and maybe we will give some bonus codes that you can run to see this. Okay. So, one important thing for us to remember is this: the eigen decomposition might not be unique. Okay. For example, if you have the matrix the identity matrix. So, let us take a 3 cross 3 identity matrix. For the identity matrix, every vector is an eigenvector. Why is that? Because the identity matrix has only one action. It does not even stretch, it basically keeps the vector as it is. You can think of it as a stretch by a factor of 1. I could also make up another matrix, let us call it A. So, there is no rotation at all for this matrix A, all it is doing is stretching, and it will do so for every vector. Okay. Now, one can think of a counterpart for this. If we think of a rotation matrix, it is not going to have stretching at all. Okay. It will not have stretching at all, which means really speaking that you cannot really have a real eigen decomposition, because an eigen decomposition only tries to find out those vectors which are actually going to purely stretch. So, if I have a pure rotation matrix or a pure orthogonal matrix, it is not going to have a real eigen decomposition. Okay. You can try this out for yourself. So, we are going to look at one very important idea, that of a quadratic form. Okay. Remember, when we are trying to find out the length of some vector, let us say x, the 2 norm is square root of x dotted with x, and if I look at 2 norm square, that is going to be x 1 square plus x 2 square up till x n square, which I can write as x dotted with x or x transpose x. Now, the quadratic form is a slightly weighted form of this. Okay. I will show you what I mean by that. It is written as x transpose A x. So, let us look at what this means. Suppose I have A as a n cross n matrix and x as a n cross 1 vector, then x transpose is going to be 1 cross n, which means all put together you are going to get a 1 cross 1 number, which is a scalar. So, a quadratic form, okay, a quadratic form is something that takes a matrix or takes a vector x and gives back a scalar, much like the length does, except it has a factor of a in between. Now, what does this do? If you write it out, if you write out this matrix product, you will basically get combinations of all sorts of terms. For example, let us say if x vector is x 1 x 2 and A is a 1 1, a 1 2, a 2 1, a 2 2, then x transpose A x is simply going to be x 1 a 1 1 x 1 plus x 1 a 1 2 x 2 plus x 2 a 2 1 x 1 plus x 2 a 2 2 x 2. Okay. It is a sum of every possible linear combination of this, as I have written here, x I x j a I j, a simple summation of that is called the quadratic form. We will see several uses of this as we go on through the course. Now, one important definition that sort of comes from the quadratic form is that of a positive definite matrix. A positive definite matrix is any matrix that has all completely positive eigenvalues. We also have another definition called positive semi definite. Okay. Positive semi definite means not just greater, but greater than equal to 0. Okay. A positive definite matrix has a very nice property, which is all quadratic forms. So, if you take any x at all, it does not matter which x you take, it is your choice, x can be positive or negative, whichever x you take, x transpose A x will always be positive. A simple example is the matrix A is identity. Notice identity is already a diagonal matrix 1 1 1, which means lambda, all eigenvalues of identity are 1, which means it is a positive definite matrix since all are positive. This will give us x transpose I x, since I is the matrix, is the same as x transpose x. So, this is always positive, okay, as you can say. Okay, so, for all x, of course, for all x not equal to 0, if I multiply it by 0, of course, it is trivially 0. So, a positive definite matrix has the property that for all non-zero x, x transpose A x will always be positive. A positive semi definite matrix has the property that for all x, x transpose A x is greater than equal to 0. So, you could have non-zero x which give x transpose A x is equal to 0. Okay. So, you can see a simple example of this. Let us say a matrix B, which is 1 1 0. We can find out some x transpose A x or x transpose B x, which is equal to 0 for x is equal to 0 0 1. Okay. This is a non-zero x, but if you multiply it, this term will be 0. If you write it out in this way, you can automatically check that x transpose A x or x transpose B x is equal to 0 even when x is not equal to 0. So, similarly you can define negative definite and negative semi definite matrices. So, a negative definite matrix has all eigenvalues less than 0. Negative semi definite means all eigenvalues are less than equal to 0, and similarly the quadratic form x transpose A x for a negative definite matrix will always be less than 0, and for a negative semi definite matrix x transpose A x will be less than equal to 0. Finally, we come to another decomposition. We will not be using it very often in this course, but it is a very useful idea, and it is a useful idea when we discuss decompositions. This is a generalization of the idea of factorization that we have just used. You can think of it as a generalization of the idea of the eigen decomposition itself, okay. But we can apply this idea to non-square matrices, okay. So, factorizing matrices, we had done it based on stretch and rotation. So, it is the same idea which is applied for singular value decomposition also. So, let us say A is a m cross n matrix, m which is not necessarily equal to n. So, it can be a non-square matrix, okay. So, then you can write the factorization of A as u d v transpose, where each of these have the following properties. U is a m cross m matrix, okay. So, remember A is m cross n, U is m cross m, V is n cross n, okay. So, obviously if we need to match the sizes, okay, we need a m cross D is a m cross n matrix, okay. Now, U and V have properties, remember both of them are orthogonal, which means both of them are can be interpreted as rotation matrices, okay. D is a diagonal matrix. By diagonal, what does it mean? It means that only the diagonal entries are non-zero. In case it is not square, even these elements will be 0, okay. So, off diagonal entries are 0, that we know for sure. Now, there is certain terminology here. The elements of U, this matrix U, are called the left singular vectors, and they can be calculated as if they are eigenvectors of A A transpose. Now, notice one thing about A A transpose. In case A is real, A A transpose is symmetric, and since it is symmetric, we know if it is real and symmetric, then it has real eigenvalues and real eigenvectors, okay. So, these will always be real, U's elements will always be real for any real A. Similarly, elements of V, they are just a switch, they are eigenvectors of A transpose A, and they are called the right singular values. The non-zero elements of D, okay, the elements here are given as the square root, this is the square root of the eigenvalues of A transpose A, okay. So, these are called singular values. The singular value decomposition has very similar, not the same, but very similar interpretation to what I talked about in terms of the interpretation of the eigen decomposition. You take a vector, rotate it into by the V transformation, you rotate it and D simply stretches and then you rotate it back, okay. So, you can think of any matrix A as again doing simply a rotation as well as stretching, and that is the significance of a singular value decomposition, at least as far as we will discuss singular value decomposition, often called SVD as far as this course is concerned. If time permits, towards the middle or end of the course, we will probably provide a few bonus videos with which you can actually visualize eigen decomposition and singular value decomposition. This ends the discussion of linear algebra, at least the separate discussion of linear algebra for this course. In the next series of videos, the next week we will be looking at probability, which is the next half of mathematics that we require for this course. Thank you.